Consider a film of liquid falling down a vertical plate. Liquid falling down a vertical plate. So this is a plate. Suppose this is a plate here. From this plate there is a liquid film which is falling down. Suppose this is a liquid film. This is plate, dimension L. This is film of delta thickness and the width of plate is W. This is a film. We need to find out the velocity profile and momentum flux profile. So this is to be find V velocity and tau profiles for this problem. So let's start by selecting a coordinate system. So for this, most suitable coordinate system is Cartesian coordinate system. So here we can say that Vx and Vy are equal to 0 as there is laminar flow. Now we know Vz is a function of x, y and z. Now here as the end effects are negligible, we can say Vz is not a function of y, and Vz is also not a function of z, because mass conservation is followed. That film doesn't get thinner or thicker. Film doesn't get thicker or thinner. So Vz is only function of x, and pressure is only function of z. So here let's assume first solid by shell balance approach. So let's consider a differential element whose dimensions are delta x, delta z and w. So we are taking here delta z to be just more conceptually correct. As the pressure is varying in z direction, we are not taking directly L here. But if you take L, mathematically the answer will be same. But we will see by solving it by delta z, the answer will be same here again. So as the x and y components velocities are 0, we will only use z balances. So z balances here are phi xz, which is rho vx vz. Suppose we are talking about here this liquid film, so we will give superscript L and tau xzl. Then again for phi yzl, there will be rho vy vz, both will be for L. Then tau yzl, and for phi zz, there is pressure term will come EL plus rho L VZL plus tau ZZL. So here it will be Vx is 0, so this term will go, only we will left with tau term. Here also Vy is 0. In this Vz is not a function of y, so this will be 0, whole term will be 0. Then here again Vz is not function of z, this term will be 0. We will left with PL rho VZL. Again applying momentum balance equation, we will get phi xz of L at x minus phi xz of L at x plus del x. This is momentum flux. Multiplying it with its area, we will get rate. And again for y direction, y equal to 0 minus phi yzl at y equal to w del z del x, the cross sectional area, plus phi zz at z minus phi zz at z plus del z w del x, the area, rho l g w del x del z due to gravity. This will equal to 0 as steady state is considered. So here dividing it by w del z del x and multiply by minus 1, we will get phi xzl at x plus del x minus phi xzl at x upon del x plus phi zzl at z plus del z minus phi zzl at z upon del z minus rho lg equal to 0. This term here will be 0 as phi yz is 0. So substituting the values of phi xz and phi zz using this and this equation, we will get minus, let this be phi xz only, we will get phi xz upon del x. Just substitute here the terms. So this rho L VZL will not change at Z and Z plus del Z. Those will be same. So only we will remain with this PL term. So we will directly write dou PL upon dou Z minus rho LG equal to 0. So from here, after substituting phi xz, we will get dou by dou x minus mu L dou VZL upon dou x plus dou PL upon dou Z minus rho LG equal to 0. So again now rearranging the equation, we will get mu L dou square VZL upon dou x square equal to minus dou PL upon dou Z plus rho LG. So here the V differential element that we assumed was of a del Z instead of L. So we will now understand why we took del Z and not L. So as there are two phases, air and liquid, and pressure is varying in Z direction, we will take into account the Z direction variation for air also, the pressure Z direction variation for air too. So for that we will write Z component equation of motion for stagnant air, which will be pressure due to air at Z minus pressure due to air at Z plus del Z, and we will multiply it by area, and this is again the gravity term that will come equal to 0. Then again dividing it by W del X del Z and multiply by minus 1, we get pressure at Z plus del Z minus pressure of air at Z upon del Z minus rho Ag equal to 0. Rearranging this term, we will get dPa by dZ equal to rho Ag. So we know at x equal to 0, pressure of liquid will be equal to pressure of air, and also the momentum fluxes will be equal. So, and we also know that both depends on Z direction only. So we can write dPL by dZ equal to dPa by dZ, which implies that dPL by dZ will equal to rho Ag. So substituting this into this equation, this that we derived earlier, substitute now this one equation to this equation, we get minus of mu L dou square VZL upon x square equal to minus rho Ag plus rho Lg. So this will be equal to rho L minus rho Ag, and as we know rho L is very higher than rho A. We can write rho L minus rho A is approximately equal to rho L. So we get minus of mu dou square Vz upon dou x square equal to rho G. We dropped the superscripts because there was no term of this air left, only liquid was left. So we just substituted, we just dropped these subscripts of liquid. We get this equation finally. Integrating this equation twice, minus rho gx upon mu plus c1. Again integrating it once, Vz is equal to minus rho g x square by 2 mu plus c1x plus c2. So for this equation, to solve this equation and find the c1 c2 constant, we will need two boundary conditions. So those boundary conditions are boundary condition 1, that is at x equal to 0, that is liquid air interface, the momentum flux tau xz will be equal to 0. So that implies that dou Vz by dou x will be equal to 0. So substituting this in this equation, we will get C1 is equal to 0. And boundary condition 2, at x equal to delta, that is liquid wall interface, there is no slip condition, that is Vz is equal to 0. Substituting this into this equation, we know here C1 is 0. Substituting the remaining terms, we will get Vz is 0 minus rho g del square by 2 mu plus C2. This implies that C2 is equal to rho g del square by 2 mu. Now substituting this C1 and C2 in the equation that we found of Vz, we get Vz equal to rho g del square by 2 mu 1 minus x by del whole square. This is the velocity profile that we were to found. And to find the momentum flux profile, we will just substitute Vz here with minus mu dou Vz by dou x. So differentiating, which is equal to tau xz. So tau xz will be just differentiation of Vz once with x, which will give us minus mu minus rho g x upon mu, which is equal to rho g x. That is tau xz is equal to rho g x. This is momentum flux profile, and this we found here is velocity profile. So we have found the momentum flux profile and the velocity profile for a vertical plate from which a liquid film is falling. This is a liquid film.